Hello, I have an additional addendum to my last video that I made. So in the last video, I showed you guys this is an op-amp, this is a band gap reference, and this guy here to the left is just to balance the voltages at the two drains here of my input pair. So if I run the simulation really quickly, I left off showing you guys how to figure out the stability phase margin, but there's additional things that you can do under results, annotate, which actually help you determine whether a device is in cutoff, saturation, linear. So right now I'm showing the component parameters. So if we go to annotate DC voltages, results, annotate DC node voltages. It'll show the node voltages. I showed this in the last video. I'm just doing a recap. And you go annotate DC operating points, which you'll notice, let me zoom into a pair. The operating point, you'll see, let's go down to a better one. You'll see the drain current going through here. It'll show you VGS and VDS. So here's a good example over here. So if we go results, another thing that you would be interested in knowing though is the threshold voltage. So you can print model parameters, and you click on an individual device, and this will give you all the model parameters for this one device. Now the only thing though is if we scroll down here, we have a where is it? VT naught. It only gives you VT naught. It doesn't give you the actual threshold voltage. So there's a neat tool if you go results, circuit conditions, and I set this up already. So it's pretty easy to set up. Check the box next to saturation, BJT, or MOS for linear. So this will check if your MOS is in linear. You can look for your breakdown. I added these. I added VDS, VDS set, VTH, and VGS. The way you add it is you go down to here. You choose BSIM 3v3. This represents your MOSes, and you just put it in a range. So this has a variety of things that you can look at. You can look at your transconductance per se. You can also look that has R on. You can see what type of device it is. But the ones that are very important to tell what region of operation you're in, you want to look at your VDS, your VDS sat. This is also known as your overdrive voltage. You can look at your threshold and your VGS. So in order to be in saturation, VDS has to be greater than your overdrive voltage, which is VGS minus VTH. Though what's interesting is if you do this the VDS is pretty close to if you take VGS minus VT. So there's something that it's doing a little bit different here. But if we say print, and at the very top it'll tell you that I have no devices in linear, which is good. I do have my two PMOS input pair is in cutoff, like I said, or it might be in cutoff. We can confirm that. From looking here, my VGS is 0.348 volts and 0.349.5 volts. So let's look at P3 and P4. P3, here's its VDS, and here's the VDS for P4. And so actually, remember for saturation, so these are in saturation. So sometimes it's not good to just go off the base threshold voltage. So if we notice right down here, for these two guys, the threshold voltage is actually below the 0.42 volts. So basically these guys right here actually have a different threshold voltage. So you can see the calculated threshold voltage for each of the devices here. So originally I said these two guys are in cutoff. which was true assuming that my VT did not change, but my VT did change, which is right here. So the easy way to see if it's in saturation, you look at your VDS, do the absolute value because that's just easier, and then you look at your VDS sat. Most of my devices I designed, I tried to get a VDS sat of around 0.1, so I'm pretty close. This is a higher order model, so it does a lot of other things. Also with the input pair, after I got around, I started increasing the width to try to get a bit more transconductance out of it. So actually we can go and look at the transconductance. It's typically below 1. So if we change the range and we go look for GM and we add, then when we print, and it'll update the list. And what you'll notice, so here's my transconductance here of my input pair. So what you can do is you can mess around with the sizes, and but usually what I end up doing is I don't really, for this class project, you don't really need to worry about that too much. Also, this additional current mirror, if you notice, I'm pressing 9 to show what's highlighted together. This guy, these are all connected together, and I don't use this reference here at all. That's not connected to anything. So 9 is a good way to see what's connected, and Control 9 gets rid of it. What this guy is doing right here is, if you notice, is I'm just trying to match the currents and voltages here very well. So this guy is basically bleeding in current or bleeding out current depending on the conditions of the input pair. Anyways, this is addendum to my last video. If you guys have any more questions, I'll make more videos in the future.